I'm curious. I am curious. Curious
by nature.
Welcome to Curious by Nature. I'm Jessica Johnson from Newswise. What if the cure we need for a deadly condition is already sitting on the pharmacy shelf, just waiting to be matched to the right disease? A whole field of research has emerged with the goal of repurposing an existing drug for a different disease than the one it was originally developed to treat. Now, with the potential of AI to scan billions of possible drug-disease combinations, this area of research has been turbocharged. Some believe it could transform how medicine is practiced. We'll talk about multi-system organ failure, drug repurposing at scale, and the surprising number of proven therapies that are gathering dust simply because no one is spreading the word. It's a story about science, survival, and the untapped potential of what we already have. Welcome, Dr. Fajgenbaum. Please introduce yourself.
My name is David Fajgenbaum. I am co-founder and president of everycure, and I'm also a physician scientist at the University of Pennsylvania. I'm curious about how many approved drugs can treat more patients and more diseases they're not intended for.
Newswise distributes news and research to the media, and I saw the press release from Penn Medicine, and I was really intrigued by it. And at the first sight, I thought, okay, I would really love to hear more about this for those purposes of your curiosity as well. I was curious about it. And then I saw even within the story that there was a second big story that you had treated yourself for Castleman's disease, and you found that therapy for Castleman's disease. So first of all, could you tell me what is Castleman's disease?
Sure. Castleman disease, where your immune system attacks your vital organs until they shut down, and it's oftentimes treated with chemotherapy. And when I was diagnosed 15 years ago, there were no approved therapies. Fortunately, there's been a lot of advances, but it's this relentless condition where your immune system gets out of control. The therapy we discovered that we shared in the New England Journal of Medicine article is a drug that targets a protein called TNF. The drug's called adalimumab. It's a TNF inhibitor, which is typically used for ulcerative colitis and a number of other autoimmune diseases, but it had never been used before for Castleman disease. We did a series of studies. One of them was in the laboratory, where we were looking at various immune cells from Castleman's patients that led us to think that this thing TNF might be important. Another one was something called proteomics, where we measured thousands of proteins that also gave us a TNF signature. And then maybe the thing that was most interesting to the readers of the article was that we also looked to see what our AI platform that we are building through a nonprofit called everycure that I mentioned, to see what drugs were predicted for Castleman disease by the AI platform. And amazingly, the number one predicted drug for Castleman disease was a TNF inhibitor. And so this combination of an AI prediction, laboratory experiments, and proteomics data all pointing towards TNF led us to recommend the first ever use of a TNF inhibitor for a patient who was getting ready to be transferred to hospice care, and he responded incredibly well and is doing great.
What does that therapy though look like, the use of the drug? Does someone who has Castleman's need to take it continuously? Or is it just an initial period of usage?
Well, this was the first patient ever, and we actually haven't, as far as I'm aware, have treated other patients. I do expect that the publication of this paper is going to lead, and has probably already led, to other patients being treated, but we have very limited experience. The expectation would be there would be ongoing treatment. Most of these drugs that modulate the immune system for autoimmune diseases, you tend to have to keep treating them even after the first dose, may even get them under control.
But your treatment, when you treated yourself.
So this was back in 2013. I got sick in 2010, and over the next 3 years, I was in and out of the ICU. I spent months in critical condition. I even had my last rites read to me when I was 25. It was November of 2010. So doctors were sure I wasn't going to survive. But during about a 3-year journey of surviving and getting sick and then getting involved in research, I ended up discovering that a communication line in my immune system was turned into overdrive. It's a communication line that helps your immune cells to turn on into like a fight mode. And I thought that maybe we could turn that communication line off with a drug that's been around for decades called sirolimus. And I began testing it on myself in January of 2014. So it's been over 11 years now. I'm doing great on it.
So you found then, I guess, an improved drug.
So adalimumab is, and I don't know if I would say it's an improved, but certainly there's people with Castleman's who get better on one drug and don't get better on another drug. And so it turns out that this patient adalimumab, or this drug adalimumab that we used for this recent patient, turns out that that patient wasn't responding to anything else. So chemotherapy wasn't working for him. The drug that saved my life wasn't working for him. Even other drugs that we've discovered in advance also weren't working. And so this was sort of the Hail Mary last ditch effort that worked for him. And so I don't know if I would necessarily say it's better than the things that we've discovered before, but for that patient, it was the only thing that worked.
So you really discovered two medications that work for Castleman's disease.
Yeah, even more than that, we also discovered a drug called ruxolitinib that works for Castleman's that is we're launching a trial of this year. It's a JAK inhibitor. We've also collaborated with colleagues to advance a drug called thalidomide, as well as a drug called Velcade for Castleman disease. We've advanced the understanding around another drug called rituximab for patients. So we've been able to make a lot of progress. I got sick 15 years ago. I started a foundation 13 years ago and started working on this in the lab 10 years ago here at Penn. And I'm so proud of the progress we've made.
You were one of Time's 100 health people in
Yes.
2025.
Yeah.
And so they said that you had gone after an exam that you had in med school, you were feeling really badly, and you went and your doctor told you your organs were shutting down,
Yeah.
like almost all of them. First of all, what does it mean when a doctor tells you your organs are shutting down? What does that mean exactly?
So yeah, he walked in the room, he'd run blood tests on me, and he said, David, your liver, your kidneys, your bone marrow, your heart, and your lungs are shutting down. So if you go back to liver, so that was my albumin levels were really low and my liver function tests were really high. So that means that like not good. Kidneys, it means that your creatinine levels are really high and your kidneys just aren't working. The thing that they're supposed to be doing were not working. Your heart, that was my ejection fraction was very low, so it wasn't contracting the way that it's supposed to. My lungs, my pulse oxygen levels were low around my body. And so basically it was this collection of vital signs and blood tests where he's looking here at like what looked like or was previously a healthy third year med student. I'd been treating patients and was healthy a few weeks before, and is basically looking at the lab tests and the vital signs and saying, these vital organs, the organs that keep you alive, they're not working.
It seems like it was an extreme. It wasn't just one organ, it was many organs that were all shutting down. That is
In
that
medicine,
Castleman's disease does is shut down a lot of the organs.
vital organs, exactly. Yeah, and it's sort of like, yeah, and I think it probably is confusing to describe it that way as like organ shutting down. It's like, well, which ones? But the term that we use in medicine is often called for this. It's called MSOF, multi-system organ failure, and so it's like basically saying that like you're so sick that all of the things that are keeping you alive, they're all shutting down. You know, the system is crashing. And yes, that happens in Castleman's, in particular my subtype, which is the most deadly subtype called Tafro. Within a matter of days or weeks, everything shuts down. And it's because your immune system is just destroying everything.
Currently, is your research mostly focused around Castleman's disease and therapies for that? Or do you have other topics that you're working on?
Yeah, there's really three categories. There's the Castleman specific research, which we do a lot of here in the lab, and then there's related inflammatory diseases that are like Castleman's. So, Poem syndrome, HLH, are a couple examples of related diseases. So we study these related inflammatory, and then the third category is drug repurposing, where we're not focused on a certain type of disease, but we're actually looking across all drugs and all diseases to look for the best opportunities to help people. And so, yeah, all three of them are major areas of focus, and I split my time between them.
How you find ways to use drugs that are already FDA approved for other diseases?
The way that we've been doing it in my lab for the last 10 years is basically to do really deep investigation or profiling of samples from a given disease. So maybe Castleman's, we'll look at all the proteins in the blood, or we'll look at the cell types that are in the lymph node, or we'll look at cell types in the blood, and basically do this sort of deep profile and just figure out what's going wrong when you're sick. And then we ask the question, is there a drug that can turn that thing on or off that's the problem? So like for me, we figured out mTOR was in overdrive. So then we said, well, is there an mTOR inhibitor? And there is. So let's try that. And that's what worked for me. We've done it with JAK inhibitor. We've done it with TNF inhibitor I mentioned. So that's one approach. What's going on, and then is there something to turn it off or turn it on? That's the problem. The other approach that we use is through that nonprofit everycure that I mentioned, where we use an AI platform that systematically looks across the world's knowledge on all 4,000 drugs and all 18,000 diseases. And so it's basically asking the question, if you were to try every single drug to treat every disease, then there would be 75 million attempts to treat every disease with every drug. And we use an AI platform to basically quantify how likely is it that any one of those 75 million is going to be better than any other one. And so you get a score from 0 to 1, with the 0.99s being very likely to work, the 0.001s being unlikely to work, and everything in between. And so now AI can tell you, like, these are the things that are likely to work. And then us humans can look at the things at the top and say, wow, leucovorin for autism, lidocaine for breast cancer, these are really interesting. Let's look into them further. And then we might study them in the laboratory, we might study them in clinical trials. And in some cases, we might just go out to raise awareness because the work's already been done to prove that they work.
And so is that like an open source platform that many doctors can use?
It's not open source yet. We're using it for internal purposes right now. Basically, we use it to find promising opportunities, but by April of next year, we will be open sourcing it so anyone can use it. And the only reason that we're delaying 9 to 12 months to do that is that we feel this responsibility that we want it to be as accurate as possible by the time we release it to the world. It'll be, millions of scores, lots of treatments, and we're excited that it can empower doctors and patients to think about what are other alternatives. But we also recognize that there's a big responsibility to make sure it's as accurate as possible.
Do you also use genetics as part of like the information that you include or that you're looking at in terms of how it affects a drug?
That's exactly right. Yeah. So there's a lot of genetic data that's built into our analytical pipeline. So I mentioned that we basically evaluate every drug against every disease. And the way we do that is we use something called a biomedical knowledge graph, which is like, if you could imagine, if you were to map every disease, every gene, every protein, every genetic variant, like everything that we know about all of medicine onto one map, and you were to connect them all with lines to say, this gene has increased expression in this disease, and you've got lines connecting them all. That's what we start with. And then we train, and that includes all the genetic data, to your point. And then we train algorithms, and we say siltuximab treats Castleman disease. I'm going to train you on the pattern of connections between siltuximab and Castleman disease, and insulin treats diabetes, train you on the pattern of those connections. And then we release the algorithm on the rest of the knowledge graph and say, find patterns that are similar to the known treats and give them a high score. If they aren't similar, then give them a low score. So we sort of teach the machine learning platform, like, this is a good treatment, find things like it.
So another thing I wanted to say is, after reading about the therapies that you're working on, I mean, basically, if I Google Castleman's disease and what it doesn't seem to portray what you have, what are the therapies? At least that's what I could tell at first sight, but maybe I'm wrong. Have you noticed that as well?
I don't know. I think that there's one resource called UpToDate, and UpToDate is like the home base for all of how do you treat diseases. And so I know that UpToDate has these treatments that are discussed, and so doctors that go to UpToDate should be getting them. I think that Wikipedia is probably okay. It's a little depressing, but Wikipedia is like the second most utilized resource by doctors, which is sort of a little crazy.
Yeah.
So I think that the two big ones are pretty accurate, but I'll do a Google and see what other treatments are coming up.
It says, depending on the type and severity, it's treated with surgical removal of affected lymph nodes. That's kind of like the highlighted Google thing. And so that seems a little strange when there are all of these therapies.
Yeah, so the surgical one only works for what's called unicentric Castleman disease, and so I have what's called multicentric Castleman disease. So surgery isn't even an option, unfortunately.
Sometimes I wonder how much that information is able to get to the people that need it, and what
You're so right.
ways that they find out about it. So
You're so right. It's folks like myself oftentimes take for granted that, oh, a big trial's been done to prove this thing works, therefore patients are going to get it. But to you, obviously, you work in communications, and you know that just because something is true doesn't mean people are going to hear about it and actually be able to act on it.
or how maybe doctors communicate about it sometimes, like a
Yeah.
Practitioner or something, right?
Yep, I agree.
What if someone has another disease, not Castleman's, but something else that might be not affecting many people? It might be kind of a rare disease or not. What would you suggest they do to kind of look at that and to see, are there existing options? Are there possible other drugs? How would you approach something currently being in the position knowing you had it, but maybe other than a Castleman's disease?
So I think the first thing is to talk to your doctor and say, "Hey, are there any other drugs out there that maybe even if they only have 1 or 2 cases, but, like, are there drugs out there that have been tried for my condition that you think might be helpful?" So I always start with the doctor. Depending on what she or he says, you might consider then going to this website PubMed and typing in the name of your disease and maybe the word treatment and see, are there things that show up that maybe your doctor didn't mention? And you could bring it to your doctor during your next visit. There's also a website called txgnn.org. You could go there and you could type in the name of your disease and get some scores for drugs that might be useful for that disease. That's similar to the platform that we'll be launching in about a year's time. And if you're still aren't finding things that are particularly promising, it's important to know that for some of these or many of these rare diseases, there's very little research that's being done, and as a result, you might actually have to do research, like not just reading research, but actually laboratory research in order to move things forward. And that doesn't mean you have to do it yourself, but you might need to find a lab that can do an experiment, or you might need to fund a lab to do experiments. But there's a lot of rare diseases that are neglected that really do require, for me, in order to discover that sirolimus could save my life, I couldn't look it up online. I had to run experiments on my blood and on my lymph nodes, and that's what really uncovered and saved my life.
Can you tell me more about recent work that you're doing?
A couple example repurposing opportunities we're excited about. One of them is with a vitamin derivative called leucovorin. It's FDA approved for people that are on 2 different types of chemotherapy. It's basically given along with chemotherapy as of right now. But there's data to suggest that it can help kids with autism who have antibodies that prevent folate from getting into their brain. And so as a result of this folate blockade, they don't have a typical a speech development. And what's amazing is these 3 trials have shown that if you use this drug or medicine, leucovorin, that you can improve speech and verbal communication in these kids with autism, which is just so exciting and incredible. It's something that children with autism and family members of people with autism often say is one of the biggest challenges, is being able to communicate with the world. So that's one we're really excited about advancing forward. Another is with lidocaine and breast cancer. We've learned that a large trial was done in India where women who had lidocaine injected around their tumor before surgery had better outcomes at 5 years versus those who did not have the lidocaine injected, which is again really exciting. That something as simple, lidocaine is the numbing medicine you get when you go to the dentist, for example. The idea that that could actually reduce risk of metastases and also death at 5 years is just incredible. So we're actually studying that in other cancers as well to understand, are there other cancers that could benefit from lidocaine? So these are just a few of the examples where we found an old drug that could be useful in a new way that we're really excited about.
That is fascinating. I found recently, and because a very good friend of mine, she's a breast cancer and melanoma surgeon, and often then they have to go back in and cut again. The surgeries for breast cancer can be one after the other in order to get the perimeter area. The cancer cells kind of gravitate out, or in a way try to escape. And I saw this journal article that showed that a doctor, was infected, and it was like in the New England Journal of Medicine or something like that, that was infected because they didn't have a glove on, and they got infected and they got the same genetic type of cancer on their hand.
Yes, I saw that too, and it seemed like it really caught my attention. I guess the big takeaway is that there were certain factors that like enabled that to happen that, maybe we as humans had never seen anything like that happen before, but I guess a lot of things align. I think he had maybe a cut on his finger or something like that. And also I think that there must have been enough similarities to them genetically that his immune system didn't immediately destroy it. It just, a lot of things came together, I think, for that to happen, but it was really striking.
It's kind of, I guess, relevant to that, like, numbing them so they can't really move in a way, right?
Yeah, that's part of the thought is that it directly kills some of them and that it sort of almost paralyzes other ones.
Are there things that come up and surprise you, and what are some of those things?
Yeah, I think that I mean, one of the things that I've been very surprised about over these last few years is the large number of drugs that we call unsung heroes. And what we mean by unsung hero is that the work's been done to prove that the drug works for that disease, but it's still not being used for patients. Like it's an unsung hero. It hasn't gotten the attention it deserves. I was somewhat under the impression that, if the work's been done and it works, the patients are probably going to benefit from it. But actually, there's a gap between doing the work and then getting the word out. Drug companies are very good with their sales forces getting the word out, but there are a lot of drugs that are generic where there is no sales force to get the word out. There is no incentive to find, to really push additional uses of medicines that are old. And so I think that I've been very surprised by the number of these opportunities that are really hiding in plain sight. And then I think that you could also say that been quite surprised by uh, how incredible the sort of the growth of artificial intelligence and the speed at which it can move. When we first built our platform 2 years ago, it took about 100 days to look across all of the world's knowledge and get scores for every drug versus every disease. 100 days. And now it takes about 17 hours, and so we can iterate in ways that would never have been possible even just 2 years ago.
What made you want to study medicine?
So I decided to go into medicine after my mom was diagnosed with brain cancer. So right after I got to college, my freshman year at Georgetown, just a couple weeks after, I found out that she was diagnosed with a really horrible form of brain cancer. And the moment she was diagnosed, I was like, I want to go into medicine to help people like her. And she passed away about a year later, and that made me even more motivated. Yeah, that's what drove me is to I want to take care of people like her. I want to discover drugs for patients like her. I sort of dreamed, that maybe at one point in my career, I might be able to take one new drug forward for brain cancer or for another cancer. And that to me seemed like the greatest impact that one could possibly have is to take one drug forward for one disease, which in reality, that only a very small fraction of all scientists ever get the chance to, or medical scientists ever get the chance to do that. And what's so amazing is that ever since I went through my journey and I decided that I wanted to commit my life to trying to find new uses for old drugs, I've now been able to be a part of taking 14 drugs to patients that would have never been treated with those medicines. And at this stage of my career, which just sort of goes to show a lot of these drugs are already out there. They can be used in new ways, but the work's just not being done to match them.
You went to med school and got an MBA at Wharton.
That's right.
How is this possible? How can one person do all of these things? I mean, you have this athletic ability, business ability, medical ability. So I'm really, really curious about how you did that.
I think that the best way to describe sort of how I got through those things and how I've gotten through challenges since then is that I always have a very clear focus on what I'm working on. It's like, what is that thing that I'm working towards? Right now, it's repurposing drugs for diseases. But what is that thing I'm working towards? I always have an amazing team beside me. So whether that's the 20 members of my lab who are here, or the 50 members of everycure that are part of that team, or it's my family, or back then it was my girlfriend. I always have an amazing team that I work with. And the third one is I work really, really, really hard. Like there is no balance in my life. I work nonstop. And so I think that I think those are probably the three things that have helped me to overcome a lot and to be able to do things that I dreamed of, but that I didn't know if they were possible. But it's through those three things.
Do you sleep?
I don't sleep all that much. No, I don't.
I can imagine. Okay. And I mean, how does one go to med school at Penn and go to Wharton?
Yeah, well, it's a combined program, so I'm not the only one who's done both, but it's a combined program, and it's I think so important. I loved being a part of it. There's in med school they teach you how to take care of the patient in front of you, and they don't really teach you about the system around it. And in business school, you learn all about systems. And so, how does the system work? How do we create incentives and get people to work together? And so it felt like this beautiful marriage between, laser focus on the patient versus this really macro view. And I actually enjoyed bringing both perspectives to one another. So like in business school, I would try to bring the patient perspective to these discussions. I'd be in these, healthcare innovation courses, and I love being able to bring that patient perspective.
Now, that makes a little bit more sense that there's this combined program, but that still, I mean, it is really incredible. So many different areas. You say you're focused. I guess you're focused completely at specific times on certain things.
Yes, my focus has shifted over the years. There's always one thing that I'm locked in on, and everything's in service of it. So even when I was in business school and in medical school, what I was fully locked in on was to discover a drug to save my life. And shortly after I discovered a drug to save my life, it was discover more drugs for Castleman to save more lives. And so even though I was doing business school and medical school at the same time, they were both in service of discovering a drug to save my life. And then more lives. And so it's sort of, there's always some broader focus, but sometimes it requires multiple initiatives to get there.
Okay, so now that you are here and I have the ability to ask you this is a constant issue in my life that I'm wondering about. And so someone like yourself who is managing so many different things, how do you manage your email inbox?
That's one where I've certainly struggled. If you've emailed me in the last month, then you probably got an auto reply, because right now I actually have an auto reply that's got like 15 different members of my team. That's like, if you were a Castleman's patient, please email this person. If you were a patient with another disease, please email this person. If you were a researcher, email this person. Because I hate to be the bottleneck. So in many cases, these patients who are reaching out to us are so sick and they need answers right away. And the idea that not being able to manage my inbox, like you mentioned, which we all struggle with, could be the difference between someone getting a treatment or not getting a treatment, has led me to create this, auto reply. At some point I'm going to get rid of my auto reply, but just, that every second counts for a lot of these people. And so I try to be responsive, but I know that even my best efforts, I can't be fully responsive. So that's not a full answer to your question. I guess maybe the direct answer to your question on how I try to do it, that's sort of how I apologize for not doing it well, but how I try to do it is that every email sort of falls into three categories. There's the needs to be replied to now. So as soon as I see it, it's like, I remember hearing this motto once, Ohio, only hold it once. Like some emails are like, you have to reply to right away. Some emails get starred, which means that they need to get replied to hopefully in the next week or so. And then other emails that don't get replied to right away or don't get starred can oftentimes get, lost into the abyss. But that's sort of my best effort. I'm interested to hear what's your strategy?
That's a good one. I use snooze a lot, but I need to only hold it once more often, I think,
Yeah.
and try to get rid of it more quickly. I think I look at them too often. And that would be my next question. How often do you look at your emails?
Yeah, I really am only able to look at emails first thing in the morning for about an hour, and then before I go to bed for a couple hours. Because during the days get busy with actual work and with meeting with people and actually doing work. And so, yeah, I probably have those are my two blocks. And your point around the Ohio for emails is that you can spend a lot of time reading emails, and then in your mind you've formulated how you'd reply, but then you put it off or you snooze it, and then you have to rethink about it again. And so it's like, I like to think about it as if you can spend as much of your time writing emails instead of reading emails, then that's a good balance.
Dr. David Fajgenbaum, thank you so much for talking with me.
Curious by Nature is a production of Newswise. More than 7,000 journalists get the Newswise wires. Visit newswise.com and find out how to spread your news today.